All right. Let's just look at the reflecting very quickly here. We're going to just go over these. How does a squared factor in the equation of a polynomial function affect the shape of the graph near its corresponding zero? Everyone should know this, right? The squared factor. So how does this affect what's happening at x equals 2? How does that? Yeah, so there's a turning point, right, happening there. Now, how does a cube factor in a polynomial function affect the shape near the corresponding zero? Yeah, it goes through and there's a flattening out. Okay, let's not worry about that last one. Okay, sketch a possible graph of the function. So this should be pretty easy now. Okay, we know a lot of things that are happening. So I'm going to do a really, well, let's just look at the one they've graphed. Easier. Okay, because it's negative and our degree is 1, 2, 4. So our degree is 4. We know that our coefficient is negative, so the end behaviors are both going down. Okay? Next, we know at these points something's happening. X equals -2, x equals 1, and x equals +3. There's stuff happening. At 3, there's a turning point. So I know it's got to be coming down like this. Okay? And then these like that. Okay, so totally different graph. Neither one is completely accurate. You'll notice it says the possible graph of f at x. Notice all of the critical points, though, we have the same. Okay, the only difference is they actually calculated the value of the y-intercept. Okay, and the way they did that is they just subbed in x for 0 and they calculated 18 for y. Okay, so they found this point. So I might have been a little off there. This is probably more like up here. Okay? Any questions now about this graph? Easy, right? All right. Number 2. Write the equation of a cubic function that has zeros at -2, 3, and 2/5. The function also has a y-intercept of 6. So there's no more guessing here. They've given us enough information to write the exact equation. And as you know, when we deal with algebra, we deal with exact solutions. Okay? So what do we need to do here? The first thing it tells us is it's cubic, and these are our intercepts. We don't know our a value, so we have to leave it as a to begin with. And then we know that we have zeros at these values, so I put in the opposite. Everybody know how I went from 2/5 to 5x minus 2, right? X is equal to 2/5, right? I'm going to try now get this equal to 0. So I do this, 5x minus 2 equals 0. Okay, that's how you go from here, an interception point, to a factor. Okay, the last part is we have to solve for a, and the way we do that is they give us a y-intercept of 6. If we know the y-intercept is 6, we know when x is 0, y is 6. So I'm going to set y equal to 6 and set x equal to 0. And then I solve for a. Okay, so my final function then looks like this. Any questions? So that's an exact value. First time you've seen an exact solution today. All right. No questions there? Okay, number 3. Write the equation of the function shown below. State the domain and range of the function. All right, so it gives us a point, very key. Okay, we don't know the a value initially, but we do know the x-intercepts. So we're going to put those in. Notice how I made them both squared because it's turning at both of those points. Okay? Finally, the last step is you plug in the value of x and y and solve for a. So y in this case is 4 and x is 2. So my final equation then becomes...
Sir, how would you know to put 2 rather than 4?
Yeah,
2 here?
No, for the equation. The power 2. Exponent 2.
Oh, because it's not like, it doesn't look like this. Okay? And you can actually check that with the step pattern if you want to go real close nitty-gritty, right? The squared x squared step pattern is 1 over 1 up, 1 over 3 up, 1 over 5 up. Okay, so you can actually see what's going on here. If I go 1 over here, I go 1 up, 1 over 3 up. Okay? If you had x to the 4, the step pattern is going to be different.
Yeah, multiply by 4.
Yeah. All right, the last part is it says the domain and range.
Excuse me, teachers, could you please send the attendance for second period at this time?
Who can tell me the domain and range of this function? So we can move on quickly. Jesse.
X is a set of real numbers.
Yep.
Y is a set of real numbers, and y cannot be less than 0.
No.
Oh, because then it equals to 0, sorry.
Yeah, it's greater than and equal to 0. Thanks. There's your domain and range.
One that I was looking right at is
All right, last. I think, no, maybe there's one more. One more, sorry. Example 4, sketch the graph. Whenever you guys see a graph like this, I'm going to tell you this once. You got to remember this. You have to factor out what's common. X cubed is common here. Any questions how I went from there to there?
hold on.
So now we know that something's happening at -2 and at 0. Okay? We know that it's a quartic function. The degree is 4. So we know that the behaviors are going up. And then we know that this order is 1, so it just passes through here. And then we know this order is 3, so there's a straightening out here happening. Yep.
Wait, sir, can you explain how you got f at x equals 3?
Yeah,
x
just
divided-
what's common here. There's x to the exponent of 3 is common in both. You got to factor it out. So x to the exponent of 3, divide both of these by x to the 3 gives you x. Divide this by x to the 3 gives you 2.
Oh,
Okay? All right. Last one. Okay, this is a graph of a dolphin jumping. It says write the equation of the polynomial function that represents the height of the dolphin relative to the surface of the water. So you have to see that there's a 0 there, a 0 there, a 0 there, a 0 there. Okay, so we don't know the a value yet. So here we set it up with a as unknown. But all of these 0 values are put in. So +2, +6, +10. Okay, and +14. Finally, this is the only area where there's a little bit of guesswork. He's saying that at x equals 3.5, y is equal to 0.5. So he's looking at the graph and he's saying here's 3.5 and here is 0.5y. Okay? So this point he's calling out. Okay? It's important when you look for a point to solve for a, you can't use one of the intercepts because you'll get something equivalent to 0 equals 0. So you have to use a different point. Might have used -3, 0, the y-intercept, to solve for a, but you should get the same value of a, okay? Which is down here. So he plugs in 3.5 for x and he plugs in 0.5 for y and solves for a. Any questions? Once you have a, you have the graph. Yeah.
So really what we're using, when we go to graph, like a possible graph.
Sorry, Luke, I'm just going to interrupt you and then I'll let you finish. Before I forget, I want to point out that even though this graph is, notice how you know the a value is going to be negative? Please don't substitute a as negative before you solve for it. Leave a as a positive variable and then you'll solve for a negative a value. Okay, if you put in a as like this as negative a to begin with, you'll get the answer wrong. Okay, do you guys understand that?
Yeah.
So although the graph, you know a is going to be negative, still substitute in regular positive a and then solve for it and you'll see. Okay, go ahead, Luke.
When we're looking at the functions or create a function, it says the graph it. We still don't know how to make a minimum or maximum for where the turning points are or anything like that, right?
No, you don't know exactly where they are. No, you're right. That's why all of these answers in every question, it says a possible graph.
So really,
Sorry?
really all we use the a values to see what it looks like, know where the endpoint.
No, when you're solving for the a value, you're getting the exact function of the graph.
No, I understand that, and we're using it to see what the endpoints are. Really, we can't because wouldn't that?
You're using the a value to get the function, the equation of the graph.
Okay.
So let me try and answer that again. When you're given the equation and you're trying to go to the graph, you're right. You can't get exact values of the turning points. But when you're given the graph and you're going to the equation, you can get the exact value of the equation because you read another point off the graph. Okay? All right, I know it was a long lesson, but here's the summary. The zeros of a polynomial function are the same as the roots of the related polynomial equation. That's kind of self-explanatory, right? Roots and zeros, kind of the same thing. To determine the equation of a polynomial function, follow these steps. So you substitute the zeros into the general equation. Okay, that's where they go. Substitute the coordinates of an additional point and then solve for a. Okay, we've done that a few times now. If any of the factors of a polynomial function are linear, then the corresponding x-intercept is a point where the curve passes through the x-axis. So it just passes through. When we have a square, there's a turning point. So there's a turning point occurs when the degree or the order is 2. And finally, if we have a cubic order or order of 3 or odd, then there's a straightening or flattening out on the graph. Okay, any questions?